Hello and welcome back to Total Organic Chemistry. This video I will be taking a look at some of the strengths of bonds in alkanes and stability of radicals that form. So up until now we've been taking a lot of looks at what we call heterolytic bond cleavage. And heterolytic cleavage is going to be something where the two electrons in this bond both go to a single atom. So it's an asymmetric process. We end up with two ions. We end up with a cation, in this case the hydrogen, and then an anion, where the electrons go to form this chlorine with a full octet. And heterolytic bond cleavage is very important, but for this video we're going to be taking a lot of, we're going to be studying homolytic cleavage, which is symmetric, where we have both electrons in the bond going to different atoms. So we use those single-headed arrows to show that only one electron is moving, instead of the double-headed arrow with both electrons. So in this case we end up with two hydrogen radicals. And we can just show that with H dot. So they don't have any charge on them, but they do have an unpaired electron. So I'll write this here. This is heterolytic cleavage. Hetero meaning different. And with heterolytic cleavage, like I said, we will form ions. And homolytic cleavage, homo is the same. And with homolytic cleavage, we form radicals. And some examples of maybe organic ions or radicals that we can draw. We can have maybe a cation with, from the methyl or from methane, we can have a cation that might look like this, where carbon only has a sextet, so it has a positive charge. We might also have the methyl radical, where we add one electron, so we get that single electron there, it has no charge. And maybe an anion, if we add yet another electron. So in this case carbon actually has a lone pair, so it has a minus charge here. And we'll be working with all three of these types of species in the future, and they'll come up in different situations, but they all have very similar characteristics and we can study them in similar ways. So one thing we can use to quantify the strength of a certain bond is bond dissociation energy. And we'll be talking about these quite a lot, especially when we talk about different functional groups and how they bond together. And for this, we often use DH, so dissociation, and then H is enthalpy, remember. And this is only for homolytic cleavage. So we only use bond dissociation energy to talk about the strength of bonds when they break in a homolytic fashion and not a heterolytic fashion. So for example, if we have a high dissociation energy, that's going to be a very strong bond. We're going to take a lot of energy that we have to put into that bond in order to break it. And if we have a low dissociation energy, that means that we don't have to put as much energy in to break that bond. So we can tell that that means that bond is going to be weaker. It's going to be more willing to break or more likely to break. And we can take this a little bit further. We can say that if that bond is really strong, then, for example, those two atoms really want to be bonded together. They don't want to be alone. So we can say that that also implies that the products are unstable. And conversely, if we have a weak bond, if it's not very hard to break that bond, that means that the individual atoms probably are pretty content with being on their own. So we can say that those are pretty stable products. And we'll talk about more about what that means a little bit later as well. And you can definitely think about this as well as acid-base strength, like how we discussed in a previous video on the strength of acids and bases and the factors that contribute to that. This is very comparable. We talked about if the bond, say if you have some OH bond in an acid, if this is really, really strong, if that bond is really, really strong, then it's going to be very hard to take off that hydrogen. That means it's going to be a much weaker acid. Or you could also say that the conjugate base, after you take off the hydrogen, is very unstable. So we don't want to break that bond. But if the conjugate base is very stable, and it's very easy to break the bond, it's going to be a much stronger acid. So we can kind of draw some parallels there. In terms of alkanes, which is what this video is focused on, we can look at a couple different types of CH bonds. We can have a methyl CH, where we start with CH, so CH4, and then we take a look at one of those bonds. We could also add on an R group, and we can use R a lot in organic chemistry. This is just any organic chain. So R a lot of times just represents some sort of organic chain or substituent on that carbon, where we don't really care about its identity. It could be 1 carbon long, it could be 10 carbons long, could have other things on it, but we don't really care about that. We could also add another one on, R2CH, and then look at one of those other CH bonds. And then R3CH. And then if we imagine breaking each of these CH bonds in a homolytic fashion, we can again draw our arrows, single-headed arrows to show that that's homolytic cleavage. We'll form a methyl radical here, so CH3 dot. CH2R, we're taking one of those hydrogens off again. And then similarly CHR2, and then maybe CR3 dot for this last one. So these are the couple different types of radicals we could make. And we have names for these. This is a methyl radical. This is called primary. So primary is 1, right? And this means that we have one substituent, one carbon substituent on the carbon that we're looking at. This is secondary, because we have 2 substituents here. And if you can guess, this is tertiary. And these radicals we can categorize into each of these names. So methyl radical, primary radical, secondary radical, and tertiary radical. And what we can say is that this tertiary radical is going to be the most stable, whereas the methyl radical will be the least stable. And remember what we said up here is if we have a very low stability product, so the unstable product here, that's going to mean that we have a strong bond to break. So this is the strongest bond between carbon and hydrogen. And we can also tell that this will be the weakest bond between carbon and hydrogen. And this is supported by empirical data that we can collect. We can measure the strengths of these bonds, how much energy it takes to break them, and it does indeed agree with this. It shows us that the tertiary radicals are the most stable, and they have the weakest CH bonds, and something that's methyl has the strongest CH bond and the least stable radical. So you're probably wondering why is that the case? Well, it has something to do with hyperconjugation. And hyperconjugation is a very fancy way of saying that the orbitals in a certain radical or a certain molecule will overlap slightly. And when those orbitals overlap, they're going to donate a little bit of their electron density. For example, if we have our methyl radical here, we can draw C and then H, second H, and then maybe a third H. And in the radical, remember carbon only has a sextet. So what happens is it actually has an open p orbital here with the single electron from the radical in that p orbital. And this is sp2 hybridized because we only have 3 substituents. We only have the 3 hydrogens bonded to that carbon. So that means it's going to have to be sp2 hybridized. And remember that sp2 hybridized carbons are planar. So we can think about these hydrogens as being in the plane, all in the same plane, and then this p orbital here is coming out of that plane. It's perpendicular. In this case, there's no extra orbitals to overlap into that p orbital. However, if we look at something that's not methyl, maybe we have a primary radical here, where we have another carbon attached to that first carbon. And then let's say this carbon is sp3 hybridized. So it's going to have the sp3 orbitals here. And then our first carbon is going to have that p orbital. I'll specify that over here as well. P orbital. P orbital. And if we draw our single electron here from the radical, and then in this case we could imagine this is just another methyl substituent, so we have a CH3 group here. And each of those bonds is going to have 2 electrons. We know that. But in some cases, these orbitals can kind of overlap. And that overlap of the orbital, because we remember that orbitals they don't have a clear boundary. It's sort of an electron cloud where the density is spread out over a certain area. So in certain cases, these electrons from the substituent will overlap into the p orbital of the radical, and it will stabilize that radical to some extent. Because that radical the electrons want to be paired. Electrons don't like to be lone, they don't like to be singular. They're much more lower in energy when they have a pair. So donating that electron density will lower the energy of our system and will make our radical much more stable. So more overlap, more stable. And so what type of radical is this? This is going to be a primary radical, right? It has one carbon attached to this carbon where the radical actually is. And if you kind of think about extending that analogy, we have secondary carbons with even more overlap, where we can have multiple orbitals overlapping into that radical, or even a tertiary carbon, a tertiary radical that's going to have a lot of overlap and therefore very stable. So that means that we can remember, and this is going to come up very, very often as we move towards, we move further in organic chemistry and look at more types of reactions. Tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. And right now we're talking about radicals, but we will find out that we can actually use similar ways of looking at this to apply to different systems as well, maybe cations or anions. So one thing I do want to talk about is a consequence of this stability and this bond dissociation energy that we've been talking about and how that applies to the real world. So you might have heard of a certain class of compounds called CFCs. And CFC is chlorofluorocarbon. CFC. And chlorofluorocarbons are any sort of organic compound where, very intuitively, I think, we have carbons that are attached to both fluorine atoms and chlorine atoms. And you might also know that CFCs have been outlawed in certain places and basically phased out of use because of their detriment to the atmosphere and the damage that they can cause to the ozone layer. So how does that even happen? Well, if we put one of these molecules in the presence of UV light, so there's a lot of ultraviolet light in the atmosphere, and if we release these compounds into the atmosphere, that ultraviolet light can actually cause homolytic cleavage. So we can imagine this bond right here between the chlorine and the carbon breaking in a homolytic fashion. Remember, homolytic cleavage is going to form radicals. So we end up with a carbon radical here, and then maybe a chlorine radical as well. I'm omitting all the lone pairs, but I hope that you can understand where those lone pairs are. If you need some more review on drawing Lewis dot structures, you can take a look at my video on Lewis dot structures and bonding. So this chlorine radical right here can go ahead and actually react with ozone in the air. So O3 is ozone, and ozone is very important for trapping ultraviolet light and protecting us from the sun's ultraviolet light rays. And it can actually form oxygen, just regular oxygen gas, plus some sort of ClO radical. And this ClO radical can go and react with more ozone and keep this process going. It's a chain reaction. So that's why these radicals are very detrimental to the atmosphere. They're very harmful to the ozone layer because ozone is easily broken into oxygen that way. So why, you might be asking again, why is the chlorine breaking off and not the fluorine? Well, the fluorine, the CF bond, is much stronger than the CCl bond. And you might be able to think about that intuitively. Chlorine is much larger and it's less electronegative than fluorine. So we can see that that bond's probably going to be a little bit longer when it's bonded to chlorine, and it's probably going to be a little bit easier to break that bond. And for that reason, a lot of the compounds that are chlorofluorocarbons have been phased out, like I said, in favor of compounds that only contain CF bonds, because the CF bond is incredibly hard to break. It has a very high bond dissociation energy, which means that it's going to be very hard to get those fluorines to come off and react with anything. So something like Teflon, for example. Teflon has only carbon-fluorine bonds and no carbon-chlorine bonds, which is very important to our environment and to our atmosphere. So that's all I wanted to talk about for this video on the stability of radicals in alkanes. Thank you again for looking at total organic chemistry. Please feel free to subscribe and like, as well as check out my Patreon page. I will link that in the description.